Hello, everyone. Today, we discuss an identity, the sum of two nested cubic roots of polynomials equals 1. We want to prove that for all x greater than or equal to -5/8, the cubic root of ax plus square root of bx plus the cubic root of ax minus square root of bx equals 1, where ax is a linear function 3x plus 2, and b of x is a cubic polynomial x plus 1 squared times 8x plus 5. Our first impression is that the equality is just an equation with only finitely many solutions. However, it is indeed an identity. It is true for almost all real numbers in the domain. Let's look at some examples. We plug in x equals 0, 1, 2. We got 3 equalities. They are all true identities. You might have watched some YouTube videos dealing with these individual equalities already. Let's try some smaller numbers like negative fraction. X equals -1/2. Plug it in. We got a trivial identity. X equals -5/8 is a boundary point. In other words, it is a 0 point for the function b of x. The function b of x has another 0, -1. b of -1 equals 0. However, -1 is already less than -5/8. It is out of the range of our discussion. It's no longer valid. However, I just want to remind you, remember this point. We are going to revisit this point later in the video. Here's my agenda today. First, I'm going to solve the problem, and then I will extend the identity to complex numbers. And finally, I will give some background with a discussion of an old IMO problem. The strategy is that we want to solve the identity, treat it as an equation, and see for what x the equation holds. Then we first need to know the domain of the question. We have a square root for bx, so we need b of x is greater than or equal to 0. Therefore, the domain is x equals -1 or x greater than or equal to -5/8. We already tested x equals to -1. This is not a solution. So from now on, we focus on x greater than or equal to -5/8. First, we introduce 2 new variables. Let u to be the first cubic root, and v is the second one. Then immediately, we have u plus v equals 1. This is the equation. Moreover, we calculate u times v, the multiplication of the 2 cubic roots. Inside the cubic root, we have ax plus square root of bx times a of x minus square root of bx. Therefore, we have a cubic root of ax squared minus square root of bx squared, that is bx. Plug in the polynomial, expand it, and combine the like term, we got this. This is actually a perfect cube. It is actually, the cubic polynomial is actually the cube of negative of 2x plus 1. Now, we have u plus v equals 1, u times v equals negative 2x plus 1. We can solve for u and v in terms of x. Actually, you can use method of substitution or use Vieta's formula. We have uv equals these two expressions in terms of x. At this moment, we don't know which is u, which is v. Let's test. We pick the first root, 1/2 plus 1/2 times square root of 8x plus 5. Calculate the cube, the third order. We factor off 1/2 to the third order is 1/8. And then expand using a binomial formula. We got 4 terms. Some of them are just, 2 of them are just polynomials, the other 2 contain square roots. We combine the like terms. Polynomial combined together and the square root combined, we got this. And then we cancel out the denominator, we got 3x plus 2 plus square root of x plus 1 squared times 8x plus 5. This is exactly a of x plus square root of bx. So in other words, the first solution is actually u, and then the other one is v. Now, we know actually the 2 analysis cubic roots can be simplified. So the new equation is like this, and we want to solve it for all x greater than or equal to -5 or 8. It is true identity because the positive and the negative square root cancel out. We got 1/2 plus 1/2 equals 1. Let's look at an example. So the first one, we plug in x equals 0. We got cubic root of 2 plus square root of 5 plus cubic root of 2 minus square root of 5 equals 1. If we use the second equality, it is actually 1/2 plus 1/2 square root of 5 plus 1/2 minus 1/2 times square root of 5 equals 1. In other words, the first cubic root is actually 1/2 plus 1/2 times square root of 5, which is the golden ratio. So we not only prove the identity, we actually find the simplifications of all cubic roots. Now, let's go to the next topic. We extend the identity to complex numbers. In other words, when x is less than -5 over 8, we got the square root of negative numbers, which is complex numbers. We want to examine the equalities under these assumptions. Now, let's revisit the case for x equals -1. The first identity, so remember when we plug in -1, we got cubic root of -1. On the right-hand side, we got 1/2 plus 1/2 times square root of 3 times I. And we have another cubic root of -1 equals 1/2 minus 1/2 times square root of 3 times I. If we only consider real numbers, we know cubic root of -1 is simply -1. But if we expand the domain to complex numbers, we know these two complex numbers are indeed cubic roots of -1. In this case, the equality is true for x equals -1. In short, under the setup of complex numbers, these two cubic roots are triple valued. They have 3 cubic roots for every x. If we choose one of the cubic roots according to our identity, then the original equality holds for all real numbers of x, even for all complex numbers of x. In other words, the equality is really a universal identity holds for all complex numbers. Now, let's go to next topic. I want to give you some historical background and how I developed this problem. This is an AMO problem. The second problem in 1959. The test for 1959 was actually the very first international mathematical Olympic competition. The old problems are usually simple and easy, but also elegant and beautiful. This is an equation with 2 nested square roots of square root. The right-hand side is a constant, square root of 2 or 1 or 2. So in other words, we need to solve 3 equations. Inspired by this problem, so I extend it to nested root of higher order. That's how I come up with the problem we discussed today. We can even extend to more higher order problems, like this one, like a 4th order of cubic root ax plus square root of bx and so on equals 2, where a of x equals x squared plus 6x plus 1, b of x equals 16 times x plus 1 squared. You can try it using the technique we discussed today. Or inversely, you can also develop even other identities or even higher orders, like 5th root, 6th root. So, developing these identities is really a straightforward, very easy. I would say it's much easier when we prove them. As a conclusion, in this video, I discussed this identity from different perspectives, but still I skipped a lot of details. I have some related videos. you can watch them if you are interested. And finally, if you like my videos, please consider subscribe my channel. Thank you very much.